Welcome back to ECE 320A. Today what we want to talk about is trying to provide a little bit more intuition into the Laplace transform, and we'll do that by really just beginning with introducing this variable s, the complex frequency variable, trying to get more comfortable with that. And really it's just a generalization of what you've already done in ECE 220 with respect to phasors. Hopefully that will be a little bit more clear after our discussion. We will also try to illustrate that by means of a low-pass filter example, and then we will get into the implementation of some of these ideas or go more specifically into the inverse Laplace transform techniques that we'll be using in this course. Let's now get started with the Laplace transform. Specifically, we want to sort of try to answer the following question. What is the variable s? If you were in an interview and somebody now said, when I was a student, I don't remember what that complex, I didn't really understand that complex or that s variable that kept floating around in the different classes. And now the interviewer asks you, can you tell me a little bit about this variable s? If you were quick with a response, and maybe if the interviewer was sufficiently impressed, you might just say, well, it's a complex frequency variable. You may need to give a little bit more information than that. You could say it's a complex frequency variable that really generalizes the first introduction to sinusoidal steady state behavior that we had in ECE 220. This complex frequency variable s then generalizes the phasor concept that we have worked with in previous courses, sinusoidal steady state analysis. Contrary to maybe what you are thinking now after having worked on your first homework assignment with Laplace transforms, the Laplace transform variable s, or this whole concept of the Laplace transform, is actually designed to help us. And the reason it's designed to help us is it's trying to provide us with additional ways of thinking about the same topics, but now we can go into the frequency domain versus always living in the time domain. And sometimes when we go into the frequency domain, we don't have to play as much with all of this trigonometry and manipulating that with sines and cosines. The complex algebra takes care of all of that for us automatically, and that's one of the powers or the beauties of the Laplace transform. To get us started thinking about this Laplace transform, let's look at parameterizing that complex frequency variable s. Let's give it a real part, minus sigma, and an imaginary part, which we indicate by j. That's the square root of minus 1. And j and the real part and the imaginary part are orthogonal to one another. And again, this is a frequency variable, so we could give it the units of radians per second. Let's look at what happens, or what we can actually build from this complex frequency variable s, which is made up of two parts, a real part minus sigma and an imaginary part, j omega. If we look at what we can build with s, remember how we looked at phasors. Phasors actually started out with this e to the j omega t, this rotating phasor. If we think of S as being a generalization of the phasor concept, what happens when we look at e to this complex variable s times the time t? This is now e to the, and if we substitute in our parameterized form for s, we now have e to the minus quantity, or e to the quantity minus sigma plus j omega times time. Knowing what we do know about exponents, we can actually distribute the time variable t through both terms and then pull that exponential apart into two pieces. We can have an e to the minus sigma t piece, and we have an e to the j omega t piece. These two pieces now provide us with a little bit more insight. E to the minus sigma t. Remember, minus sigma is just a real number. Let's say that's e to the minus 2t. This simply represents an exponential decay. So part of this e to the st can be, depending on what s takes on in terms of values, it could have a piece that represents an exponential decay. The e to the j omega t should be familiar to us from ECE 220, and that's just this rotating phasor that we now have been used to dealing with. We now have this rotating phasor, e to the j omega t, that is rotating, and at possibly the end of that, or the tip of that arrow that's rotating around with a frequency of omega. So we have this e to the j omega t rotating. That tip could be decaying or shrinking towards zero, or collapsing that arrow down relative to this decay rate, e to the minus sigma t. If you wanted to think about S in terms of the complex S plane, you could think of the real part of S and then the imaginary part of S. Let's say that we had a real part of minus 2 and maybe an imaginary part of J3. And that would then correspond to a point in this two-dimensional plane that represents the real part and the imaginary part of this number. And in this case, this particular location, that dot, would be a value of s equal to minus 2 plus j3. So keep in mind, e to the st you can think of as this rotating phasor that could be either decaying, or if sigma was actually negative, it could be expanding as time progresses. We now have this rotating phasor that's decaying or expanding, and we want to now see what are the different possibilities that can come into being by the appropriate choice of S.